Hi everyone. In this video, we'll be discussing antimicrobial resistance. So let us start our journey. What do you understand by antimicrobial resistance? So nowadays, the major problem, the future threat for the humanity is antimicrobial resistance. So the reason for this is we are using them in an appropriate manner. So sometimes what happens, the antibiotics are taken for lesser duration, and sometimes the course is discontinued in between. Again, the problem is nowadays in tuberculosis, we are seeing multi-drug resistant TB, extensively drug resistant TB. So the future is to fight these resistant organisms. Now, resistance meaning is the drugs will not kill the microbe. The meaning of resistance is the drugs will not kill the microbes. Now, the resistance can be two types. It can be natural or it is acquired. Now, what do you mean by natural? Natural means from the beginning only they are resistant because the target may not be blocked by the drugs, or the metabolic pathway may not be blocked by the drugs. So that is natural resistant. For example, the drugs called aminoglycosides, they are natural resistant to anaerobes. Why they are natural resistant to anaerobes? Because aminoglycoside require oxygen to enter into the cell. Anaerobes don't have the oxygen. Another classical example is metronidazole is naturally resistant to aerobes because metronidazole has to become reduced, that is seen only in anaerobic environment. Now tetracyclines, they don't work in TB, that is naturally resistance. Acquired means initially the drugs used to kill the microbes, but now the drug is unable to kill them. So that is called acquired resistance. What is the reason? The reason is the gene become mutated. So in the bacteria or in the microbes, the gene becomes mutated. So this gene mutation will lead to resistance. There are two types of transferring the gene. The mutated gene can be transferred in two ways, either vertical or horizontal. Either it is transmitted vertical or horizontal. What do you mean by vertical? Suppose this is the bacteria. So when it divides, it will give rise to two daughter bacteria. So the resistant gene is transferred from mother to the daughter, and that is vertical transmission from above to below. That's it. There is one more concept called the horizontal transfer. So the bacteria, this has a resistant genes, and there is one more bacteria which doesn't have that resistance. So when they come closer, there is a chance that this resistant gene can go to the sensitive bacteria. So there are process for that. You would have studied that in microbiology, and that is called conjugation. Conjugation means by forming a sex pili. So there will be a tube-like thing between the bacteria, and from there the gene gets transferred. Second, the transduction. So transduction, and then one more process is called transformation. So these are the different variety of mechanisms how the gene gets transferred and how the nearby bacteria also become resistant. That is called horizontal transfer. The next important thing we need to understand is something called cross resistance. Sir, what do you mean by cross resistance? What do you mean by that? The meaning is simple. Suppose somebody is resistant to sulfa methoxazole. So a bacteria is resistant to this sulfamethoxazole. Then can we give other sulfonamides? No. Others are also resistant. Other drugs in group are also resistant. So that is the meaning of cross resistant. Right? If sulfamethoxazole is resistant, all other like sulfadiazine, then silver sulfadiazine, all are resistant to that. Now there is one more concept. The meaning is called partial resistance. So partial cross resistance. Now, what do you mean by this partial cross resistance? The meaning is, suppose somebody is resistant to tetracycline resistant, there is a high chance the bacteria are also resistant to chloramphenicol group. So tetracycline and chloramphenicol are different group. So even though they are different group, there is a chance of partial cross resistance between these two, and that is the meaning of partial cross resistance. So I told you in the same group, if there is resistance, that is called cross resistance. In the different group, it is called partial cross resistance. Sometimes there is an exception for this. There is an exception for the cross resistance. What is the exception? Let me tell you an exception for gentamicin. Gentamicin, if it is resistant to the bacteria, so then gentamicin resistant bacteria, this can be killed by amikacin. So gentamicin and amikacin are same group of amyl glycoside. See, there is no cross resistance here. So there is some exception like this. So gentamicin resistant bacteria can be killed by amikacin, but both are in the same group, right? Okay, sir, fine. The next important thing what we need to understand is the mechanism of resistance, how they acquire resistance. Mechanism of drug resistance. Mechanism of drug resistance. So what are the mechanisms of drug resistance? Let me tell you. Now this is the bacteria. I'll write the bacteria. So the bacteria has to protect itself. So what does it do? Number one, it produces an inactivating enzyme. It produces inactivating enzymes. So this is the bacteria, and it produces inactivating enzymes. So whenever you give the drug is inactivated. For example, so beta lactams are cut by the enzyme beta lactamase. So if the bacteria is producing the enzyme beta lactamase, the beta lactams will not work. Second, the group called aminoglycosides. So they will also have enzymes which will metabolize them. Then another drug called chloramphenicol. So chloramphenicol also has an enzyme which can cut it, that is called acetyltransferase. The name is called chloramphenicol acetyltransferase. So these are the methods through which the drug is inactivated. One example is beta lactams, amylglycoside, and chloramphenicol. You can remember as ABC. A for amylglycoside, B for beta lactam, C for chloramphenicol. Clear? Now the second important thing is the drug may not enter inside the bacteria only. So they inhibit the entry of drug. Classical example is the penicillin. So penicillin is not allowed inside the gonorrhea, that is gonococci. So gonococci became resistant to penicillin by stopping its entry. So that is one mechanism. The third mechanism is by throwing the drug back. Suppose the drug enters inside. The bacteria will develop a pump called efflux pump. The efflux pump will throw the drug out. So there are three mechanisms. One is inactivating enzyme. Number two, inhibiting the entry. Number three, with the help of a flux pump. So when the drug enters, the pump will push it out. So the example for that is tetracyclines. So tetracyclines are thrown out with the help of a flux pump, and that is a mechanism of resistance. Now remember, all the mechanisms may be present, but I am writing the predominant ones. Now the next thing is the drug has to go and bind to the target. Drug should work on the target. Now the bacteria are intelligent. What they do, they will alter the target. The fourth method is alteration of drug target. If the target is altered, for example, the enzyme is altered, then the drugs cannot sit, they cannot work. For example, MRSA. MRSA stands for methicillin resistant staph aureus. The problem here is the target, that is penicillin binding protein, is altered. Second, the MCQ drugs. So macrolide, clindamycin, quinpressin, dalfrestin. The target, that is 50S, is methylated. So if it is methylated target, then they cannot bind. So alteration of target or alteration of enzyme, for example, sulfonamides. The dihydrotyroside enzyme can get altered, sulfonamide cannot bind. So these are the major mechanisms of resistance. Remember, inactivating enzyme. Number 2, inhibiting the entry. Number 3, with the help of efflux pump. And number 4, alteration of target. But this is not the end of the story. The bacteria are still intelligent. Number 5, they started forming a group. So when the bacteria come in group, they communicate with each other and they pass a signal. So then they will express a gene and that will lead to resistance. So that phenomenon is called as quorum sensing. So quorum means a group. So quorum sensing is another level of resistance which is seen. And number 6, nowadays they are forming biofilm. So this group of bacteria are forming biofilm. Sir, what do you mean by biofilm? Suppose you put a catheter. What happens? Around the catheter, they form a film. So they will form a coating. And when you give antibiotics, they cannot penetrate that film and they cannot enter the bacteria. Suppose these are the group of bacteria. So they are together. What they will do? They will form a film around them like this. So this is called biofilm. So when there is biofilm, if you give the drug antimicrobials, they are not going to enter it easily, because if they don't enter, they cannot kill the bacteria. So these are the mechanisms of drug resistance. Okay, so in antimicrobial resistance, so the most important thing which has caused a problem nowadays is the production of beta-lactamase. Now beta-lactamase is an enzyme which will cut the beta-lactam ring. Suppose we are using a beta-lactam and this square type is the beta-lactam ring. So beta-lactamase will come and cut the drug. If it cuts the drug becomes inactive. So that is the role of beta-lactamase. Now there are certain drugs which can inhibit that. The drugs which inhibit that are called beta-lactamase inhibitors. So we have beta-lactamase inhibitors. I will give a classical example which we have discussed already. So what are the beta-lactamase inhibitor is clavulanic acid. So along with that, we have to give the beta-lactam amoxicillin. For example, we have tazobactam. It is given with piperacillin. So like this, we combine the beta-lactam with beta-lactamase inhibitors. Example one more is ampicillin with sulbactam. Now, the beta-lactamase are classified by Ambler. So there is Ambler classification of beta-lactamase. Ambler classification. Now, Ambler has classified these enzymes. The beta-lactamase is nothing but enzymes. The one which contain the serine and the enzyme which contain the metal. And the metal that they contain is mainly zinc. So let us discuss the serine one. Serine one, we have 3 important ones. This Ambler classification has 4 subtypes A, B, C, D. So the serine one is the Ambler classification A. Then we have the C. And then we have the D. So let us understand what do you mean by A. So A consists of narrow spectrum beta-lactamase. Narrow spectrum beta-lactamase meaning they will cut only few beta-lactams, not everyone. The next category in that is ESBL. So ESBL stands for extended spectrum beta-lactamase. These enzymes can cut penicillins, and they can cut cephalosporins, and they can also cut the monobactams. Now here ESBL producing bacteria, suppose a bacteria is producing ESBL. If you want to treat with the penicillin, it's not possible because it is cut. Cephalosporin, it is not possible. Monobactam is not possible. Then what is the drug of choice? For this, the drug of choice is carbapenem. Sir, why carbapenem? Because carbapenem are not cut by ESBL. If carbapenem is not there, what we is another idea, you can use beta-lactam. For example, you want to use penicillin, cephalosporin, monobactam. If you use that, who will cut that? ESBL. So for that, what we can add is beta-lactamase inhibitor. So these ESBL can be inhibited by beta-lactamase inhibitor. That's why we can use a combination. If you cannot use a combination, you can use carbapenem, which is not cut. So in category A, we have narrow spectrum beta-lactamase cutting only few beta-lactams, extended spectrum which is cutting penicillin, cephalosporin, monobactam, but not cutting carbapenem. That's why the drug of choice is carbapenem, or you can use a combination of beta-lactam plus beta-lactamase inhibitor. Now the problem is carbapenemase. So the beta-lactams are not cut, I told you. The carbapenem is not cut. Now the Klebsiella is also producing an enzyme called carbapenemase, and that is also cutting the carbapenem. So this is the problem what we are facing. We are getting carbapenemase producing bacteria also. So that is the story here. The next one, C stands for the beta-lactamase which cut cephalosporin. So they are called as cephalosporinase. So cephalosporinase is a type of beta-lactamase. But remember, this enzyme cannot be inhibited by the clanulinic acid, tazobactam, or the sulbactam. And the D stands for the oxacillinase. So it cuts the oxacillin, that is a penicillin. Even that is not inhibited by beta-lactamase inhibitor. So beta-lactamase inhibitors are only effective in the one, that is A category. Now coming on to the metal, and the metal, this group belongs to the B, and we call them as metallo-beta-lactamase. So we call them as metallo-beta-lactamase. Why? Because they contain the metal zinc. Now these metallo-beta-lactamase, they can cut penicillin, cephalosporin, and carbapenems. So they can cut all this. Now what they are not going to cut is aztreonam. So the drug of choice is aztreonam for this. So this can be used here, right? So aztreonam can be used for this. Now the problem is we have an enzyme similar to this metallo-beta-lactamase, and that is called New Delhi metalloproteinase. So it was discovered in New Delhi, but the patient was from other country, but still they retained the same name, New Delhi metalloproteinase. For this, the common drugs will not work, even aztreonam will not work. So for them, the reserved drugs are colistin, polymyxin, and tigecycline. These are the drugs what we can use for them. So that is the burden of problem what we are facing currently, right? So this is the Ambler classification I told you. And most of your exam question is on how do you manage ESBL producing bacteria and how do you treat New Delhi metalloproteinase 1 producing bacteria. And cephalosporinase, oxacillinase, they are not inhibited by beta-lactamase inhibitors. So what about the metallo-beta-lactamase? They are also not inhibited by beta-lactamases. Otherwise, we would have combined beta-lactamases and given it. We would have combined beta-lactamase inhibitors and given the beta-lactams. Not possible. So that is about the Ambler classification of beta-lactamase. Okay, so the next aspect what we are going to discuss is a concept called CDK. What do you mean by CDK? CDK stands for concentration dependent killing. Concentration dependent killing. And one more concept is called TDK. TDK stands for time dependent killing. So there are two concepts called CDK and TDK. And before I come to this concept, you need to understand the terminology called MBC. MBC stands for minimum bactericidal concentration. The name itself is telling you what is the minimum amount of the drug, that is antimicrobial, required to kill the bacteria over 24 hours. So there is one more thing called MIC. minimum inhibitory concentration. The name itself is telling you what is the minimum amount of antimicrobial required to inhibit the growth of bacteria when you inoculate them for 24 hours. So this is being discussed in microbiology in detail. I just told you the definitions. Now, why this MIC, MBC are important? Let me draw a graph for it. So this is the graph. So there is y-axis and x-axis. Now, any graph, you should understand what is there in y-axis, what is there in x-axis. Here we get the drug concentration, and in x-axis we see the time. Now, there is a level called minimum inhibitory concentration. So this is like minimum effective concentration what we studied in bioavailability graph. We have studied that in bioavailability graph. Only if you go above this line, when the drug level reaches above this line, the bacteria are inhibited or killed. So the drug will produce antibacterial effect after this. So when we give that, certain drugs we have to give them in high concentration. So when they achieve the peak, this peak is called Cmax. And after reaching the peak, they will come down like this. So they will achieve the peak and come down like this. These drugs, their antibacterial activity or killing activity depends on the Cmax. It depends on Cmax as well as the area under curve. So if they are above this line and if they are achieving the maximum concentration at one time, then their killing capacity is more. So the point need to understand is if the drug follows this type of killing, that is concentration dependent killing, you need not give the drug repeatedly. If you give one dose and stop, the effect will be longer. So the drug effect depends on the Cmax and area under curve. So they should achieve the concentration maximum above MIC at one point. That is fine. No need to repeat that condition. So this is called the concentration dependent killing. What is the advantage of concentration dependent killing? You can give single dose. Okay, single dose and no need to repeat. No need of repeating the doses. So you can give it a single dose or another dose, that's it. But you need not repeat it again and again. That is the advantage of the single dose or a second dose, that's it. No need to repeat. That's the point. Now another important aspect, there are certain drugs which if they are above MIC, then only they will have antibacterial activity. If they come below this, they don't work. So again you have to give the drug again, then they will kill. If it comes down again, if you keep, then only they will have antibacterial activity. So the antibacterial activity of certain drugs, antibacterial activity of certain drugs depends on the time when the drug is above MIC. So it depends on the time when the drug is above MIC. So if you are giving it repeatedly, then only the drugs will produce the maximum effect. So here you have to give the drugs repeatedly. Repeated dosing has to be done to get the full effect. Now who will follow this? This type of killing is called time dependent killing, and who follows this is a question. Now remember, in a general rule, this is followed by the penicillins and the vancomycin. Generally. Why? Because here penicillin, vancomycin, they affect cell wall, and to repair the cell wall it doesn't take so much of time. So these have to be given repeatedly. But the drugs which follow concentration dependent killing, examples is fluoroquinolones and aminoacid. Now once you give them at high dose, they paralyze the protein synthesis process, they paralyze the DNA synthesis process. To recover that, it takes so much of time. So one high concentration will produce the effect for very long period. So that's the reason you need not repeat the dose here. So that is the meaning of concentration dependent killing and the meaning of time dependent killing. So that is in brief. Now once you know this, I will give a list of drugs which follow this. I will give a list of drugs which follow time dependent killing. Example is beta lactams, I just told you. The meaning is you have to give the beta lactams repeatedly. Then you have to give macrolides, they follow time dependent killing. Then vancomycin and a drug called linezolid. So they follow time dependent killing. Sir, who follows concentration dependent killing? Now they are, I told you already, they are fluoroquinolones, then the aminoglycosides, AGs, and even though they are vancomycin derivatives, they are called oritavancin and dalbavancin. Then anti-TB drug rifampicin, an anti-protozoal drug metronidazole, and a drug which is used in VRSA, daptomycin and streptogramins. So most of you asked me a question, should we remember all these things? Just remember beta lactams and vancomycin for TDK, fluoroquinolones and aminoglycoside for CDK. Very, very important. Okay. Now the another concept what we have is a condition called post-antibiotic effect. Post-antibiotic effect. Now what do you mean by that? The meaning is in the name itself. Post-antibiotic effect means once you stop the antibiotic, will they exert the action further? Yes or no? Let us understand that. Let me write the same graph here. This is the y-axis, the drug concentration, x-axis the time, and this is the concentration of the drug, this is the time, and this is the MIC, minimum inhibitory concentration. So when we give the drug, it will go up and then come down. So when they come below the MIC, whether they follow CDK or TDK, they will have lesser antibacterial property and they don't have antibacterial property after that. Now certain drugs, they also will have effect for another brief period. After you stop this, after they come below MIC, still their effect on killing the bacteria is still there, and that effect is called post-antibiotic effect. Post-antibiotic effect is the condition where after you stop in the drug, still the effect of antibiotics remain and the bacteria will not multiply. They will be keeping quiet. So there are drugs which have short post-antibiotic effect and large post-antibiotic effect. So usually it is taken as 1.5 hours, that is 1.5 hours. If it is less than 1.5 hours, it is short. If it is more than 1.5 hours, it is long post-antibiotic effect. So because of post-antibiotic effect, the advantage is you need not give the drugs repeatedly. Because even if you stop the drug, the effect still remains for some more time. So the advantage of post-antibiotic effect is you need not give the drugs repeatedly. That's the point. Now let me tell you what are the drugs having post-antibiotic effect. First I will write the drugs having long post-antibiotic effect. Yes, so the mnemonic what you can remember for that is SMART FDC. So fixed dose combination, SMART FDC. What is S for? S stands for streptogramins and M stands for metronidazole. A stands for aminoglycosides and one more for azithromycin. Sir, you told macrolides follow time dependent killing, correct? Sir, what do you mean by time dependent killing? You have to give it frequently. But sir, we don't give azithromycin frequently. Why? Because even though it has time dependent killing, but it has long post-antibiotic effect. That's why you give it once a day. Clear? Yes. So the advantage of post-antibiotic effect is you can give them in single dose or you don't give them frequently. That's the advantage. R stands for rifampicin and T is tetracyclines. And F stands for the fluoroquinolones and D stands for daptomycin. So one more dosing of antibiotics depend on post-antibiotic effect, and C for a beta-lactam called carbapenem. C. So beta-lactams follow time-dependent killing, but even though they follow time-dependent killing, carbapenems have long post-antibiotic effect, so making them dosing once or twice daily, that's it. Now there are drugs which have short post-antibiotic effect. Short post-antibiotic effect. What is the example for that? The beta-lactams. Except what? Except carbapenems. Except carbapenems. And then vancomycin. Right. So this is the example for it. Now basically for your exam, remember it is azithromycin, then fluoroquinolones, then amyloxicillin, and here you remember beta-lactams and vancomycin. These are the things which they keep on frequently asking in your exam. So in this video, we discussed the antimicrobial resistance. Why it is important? Because now we are under the threat of antimicrobial resistance. So there are mechanisms. The drug may not be allowed inside. There is production of inactivating enzyme. If the drug enters, there is a efflux pump and there is alteration of target. Nowadays, we have a threat from beta-lactamase. I told you the amyloid classification A, B, C, D. The B is metalloproteinase, and now we have New Delhi metalloproteinase. For that, we have colistin and tigecycline. In A class, we have ESBL. For that, we can give beta-lactam plus beta-lactamase inhibitor, or the drug of choice is carbapenems. So nowadays, we have the bacteria which can also cut carbapenem. They are called carbapenems. Then we discussed concentration-dependent killing and time-dependent killing. Concentration-dependent killing, the antibacterial activity depends on the concentration and area under curve. Once you achieve that, you need not give them frequently. That is the meaning. Time-dependent killing means once the drug is above MIC, then only they will have antibacterial activity. So you have to maintain that above MIC. So that means you have to give them frequently. So please remember, CDK main drugs are fluoroquinolones and amyloxicillin. TDK main drugs are beta-lactams and vancomycin. Post-antibiotic effect means after we stop the antibiotic, the bacteria should multiply. But suddenly they will not multiply because the effect of the antibiotic still remains. So that is called post-antibiotic effect. There are drugs which have long post-antibiotic effect. If they have that much of a effect, long post-antibiotic effect, what is the advantage in the practice? We can give them less frequent dosing. If they have short post-antibiotic effect, you have to give them repeatedly. That's the meaning of that. So that is about the antibiotic resistance, CDK and TDK in this video. Thank you all.